We know that water's formula is H2O. And we know that a water molecule looks like this. In this section, we'll look at why molecules attain their particular shapes, which is important to us as we explore why compounds react the way they do. The overall shape of a molecule is determined by its bond angles made between the nuclei of the atoms that are bonded together. The VSEPR model helps us to predict the shapes of molecules. And VSEPR stands for valence, shell, electron, pair, repulsion. And the VSEPR model states that electron pairs surrounding an atom are going to tend to repel each other. And so we'll adopt an arrangement that minimizes that repulsion, kind of like these balloons. In each case, they try to arrange themselves so that they get out of each other's way. It's the same thing with pairs of electrons on an atom. Let's take a look at how all that works. The first thing we'll do is determine the electron domain geometry, which is the number of electron domains around the central atom. If you want to know the number of electron domains around the central atom, just count up how many bonding sites there are. So carbon, being our central atom for carbon dioxide, has a bond here and a bond here. Therefore, carbon dioxide has 2 electron domains around the central carbon, which makes our electron domain geometry for carbon dioxide linear. And the oxygens at either end of this carbon both have 2 non-bonding pairs of electrons attached to it. And so the dipoles that are created by these oxygens cancel each other out. And so our bond angle for CO2 is 180 degrees. A molecule with 3 electron domains, like boron trifluoride, would have an electron domain geometry that is trigonal planar. And though we would draw the Lewis structure like this, in reality, all 3 of these electron domains are going to come off of the central boron at the same angle, 120 degrees. Which means that our fluorines are going to move as far away from each other as they can. Remember the example of the balloons. And so they're going to orient themselves like that around the central boron atom. And so a molecule of boron trifluoride would look like this in terms of its shape. And so its molecular geometry is also trigonal planar. Another molecule that has 3 electron domains is the nitrite ion. And remember, the nitrite ion has resonance structures. So 3 electron domains. In this case, we have a bonding site here for a single bond, a bonding site here for the double bond, and then we have a lone pair of electrons, or an unshared pair of electrons on the nitrogen. So we have 3 electron domains, although only 2 of them are actually bonded. So our electron domain geometry is still going to be trigonal planar because we have 3 electron domains. But this lone pair, or unshared pair, that's on the nitrogen atom is actually going to be a little more of a stronger repulsion against these 2 electron domains. And it's going to push these electron domains down just a little bit, bending the molecule slightly. And so our molecular geometry is bent. A molecule that has 4 electron domains is tetrahedral. An example would be methane. And so we have our 4 electron domains, all of which are bonded. So methane's molecular geometry will also be tetrahedral. And if we look at our example of the balloons again, we would see these pairs of electrons moving as far away from each other as possible or repelling each other. And that means they would orient themselves to look like this. So our bond angles for a tetrahedron would be 109.5 degrees. Our methane molecule looks like this. An ammonia molecule also has 4 electron domains. 1, 2, 3 that are bonded, and 1 lone pair on the central nitrogen. But since we have 4 electron domains, ammonia's electron domain geometry is tetrahedral. But once again, we've got that lone pair on the central atom that's going to repel the other pairs of electrons slightly more than they're going to repel each other. And so they're going to bend these other pairs of electrons out of the way just a little bit, giving us a molecule that looks like this. And so the molecular geometry of ammonia would be trigonal pyramidal, and our bond angles will be 107 degrees. Water also has 4 electron domains, 2 pair of electrons that are bonded and 2 unbonded pair on the central atom. So, since water has 4 electron domains, its electron domain geometry is tetrahedral. And by now you're getting the idea that these lone pairs are going to bend the molecule. And so water's molecular geometry is bent. And our bond angle will be 104.5 degrees. Phosphorus pentachloride has 5 electron domains. We'd call that electron domain geometry trigonal bipyramidal. And since all 5 electron domains are bonded, we have no unshared pairs on the central atom, then our molecular geometry is also trigonal bipyramidal. Sulfur tetrafluoride also has 5 electron domains, 4 that are bonded and 1 unshared on the central atom. So sulfur tetrafluoride's electron domain geometry will be trigonal bipyramidal, but its molecular geometry is seesaw. Chlorine trifluoride also has 5 electron domains, 3 that are bonded and 2 non-bonded pairs. And so, with 5 electron domains, chlorine trifluoride will have an electron domain geometry of trigonal bipyramidal, but the 2 lone pairs on the chlorine atom are going to give us a molecular geometry that is T-shaped. Xenon difluoride has 5 electron domains, and so its electron domain geometry is trigonal bipyramidal, but we only have 2 shared pairs and 3 unshared pairs, and so our molecular geometry in this instance would be linear. See how the 3 unshared pairs of electrons come off the central atom in the same plane. 6 electron domains gives us an octahedral geometry. An example is sulfur hexafluoride, with 6 electron domains, all of which are bonded. Sulfur hexafluoride's molecular geometry will also be octahedral. Boron pentafluoride has 6 electron domains, and so its electron domain geometry is octahedral. And that 1 lone pair on the central atom is going to give us a molecular geometry that is square pyramidal. Xenon tetrafluoride has 6 electron domains, 1, 2, 3, 4, 5, 6, and so its electron domain geometry is octahedral. But the 2 unshared pairs of electrons on the central atom are going to give us a molecular geometry that is square planar. And you can see how the unshared pairs, the 2 lone pairs on the central atom, are again in the same plane. And so the VSEPR, or valence shell electron pair repulsion model, allows us to see what the shape of a molecule will be. Remember to start with your Lewis structure. Count how many electron domains you have. Consider the fact that unshared pairs of electrons on the central atom are going to have a greater repulsion than the shared bonds. And think about how that's going to affect the shape of the molecule. And that's all there is to it.